time to move on to the next step. Okay, so up to this point, we've looked at what I call big chemistry. That means chemistry that you can do in a lab and look at what's happening. So we look at chemical names, chemical formulas, then we apply them to chemical equations, and then we learn how to apply those, see what happens in different kinds of reactions, single replacement and double replacement and combustion and other types of reactions, and stoichiometry. Now, one of the things out of it is that you can do all these. One of the things that I remember when I was taking chemistry, it all just seemed sort of dry. I had to memorize formulas. I had to balance equations. Um, Nothing seemed to really tie together and have a big picture. Uh, so once I realized is that there was a big picture that really actually helped my whole vision of chemistry and my love for the chemistry. Uh, so it took a long time to do that because of the way it's taught. Usually it's taught, like I said, with memorization and just sort of you see a bunch of blips and you don't see all the blips how they all come together. Um, but once you start to see how the blips come together, you got to go, oh, that's really cool. So one of the things that you should have seen out of uh, out of all that we've talked about right now is the types of reactions that we've talked about. They all really have one thing in common, and that's oxidation reduction. Uh, every single chemical reaction that we encounter, and every one that you will encounter that has to do with electrons, is where there will be some sort of change in charge, where one species will be giving electrons and another species will be taking electrons. And that's actually why chemistry takes place, is because of that dynamic. So it just can't happen between any random particles. Okay, there has to be some sort of propensity for a particle to gain or lose electrons, and that's what we want to get into now. Uh, we want to try to figure out what atoms, because we'll start out with atoms, and you can further apply this to molecules, and we touch on that as the semester goes on. But what atoms are more easily to be oxidized? That means give up electrons. And which atoms are more likely to take electrons or be reduced? Can we predict that? Is there a pattern that we can look for? And yes, there is. Okay, and so that's what we're going to look now. We're going to look at what I call little chemistry. We're going to go down inside and look at the structure of an atom. And right now, it's a general sort of concept in all of science, is that structure defines function. So what we're going to do is we're going to come up with the structure of the electrons around the atoms, and then we're going to apply that structure to try to define how an atom behaves because of its structure. Okay, so what we're going to do is there's going to be there's four black PowerPoints that will give you the first of all, what we're going to do is what I'm going to do is tell you how this model has been developed, and then I'll have there'll be four PowerPoints about that, and then what we're going to do is that we'll sort of we'll skim aside the things that we don't really need, because this can be very, very, very complicated. And what we want to do is just get a pretty good conceptual idea of what's happening without getting into the pure mathematics behind it. Now, some of you, if you love your math, okay, please go into it. But that's quantum mechanics, which is a higher level physics course. Okay, so uh, so let's get started. All right, so just to give you an idea, this all of this is fairly new. Uh, it's all of this has taken place from about 1800. And one of the things I like to do in my classes is sort of give a history of how science has developed over the last 2,500 years. And it's interesting. I mean, it's cool how history is always cool how things develop and why things happen. And it always turns out that whenever something happens in science, it's because of what's happening around in the world, the cultural world. Um, our modern day science basically was a part of. Uh, it was bred and born by what happened in uh, the Reformation of during I believe, in the 1500s, when Martin Luther, the Reformations of the church, when he said the church is not the all of everything, and Galileo was also part of that sort of. He was the first scientist that kind of went along that same line that says science can't be taught by the church. It's got to be taught by nature and observation. And and so that sort of started all of our modern day thinking about science. And then you have the Enlightenment, and the Enlightenment. I mean, hopefully you guys had some history in your, Western history, and the Enlightenment was where they really started asking questions, and not trying to relate everything back to the church, and what made sense, and in terms of application. And out of this came, well, like our country, and our Constitution, but also the French Revolution and so forth, and also scientific revolution, uh, where science really started becoming science, and that means we started doing science, and started uh, asking questions, the right kind of questions, making a hypothesis, and doing a scientific method. And now another thing that happens in science is science sort of follows this technology. Whenever there's a new technology, usually new science, new science discoveries are made. And it turns out that new science discoveries lead to new technology, which lead to uh, new technology. So you have science discoveries will take place, and they'll lead to new technologies, and those technologies will lead to new science. So this is one of the reasons why we got to keep on doing science. Okay, if we want to develop technology, new technologies, okay, the cell phone and all that didn't just come out of nowhere. It came out of science. But where that science came out of, it came from being able to do new kinds of science based on some new kind of technology. So, so you this these guys are intertwined. You got to make sure if you don't do new science, you won't get to new technology. Okay, um, so around 1800, some new technology came around, and that was glassware, and we just go what? uh, like beakers and so forth. But the thing is that the glassware could be measured, and so we actually could start measuring things. And measuring system was developed by Antoine Lavoisier in around 1780, 1790, and the metric system. And so everything sort of was standardized. And then uh, into glassware, and then with glassware, what you can do is you can make thermometers and you can make barometers, and so you can do experiments relating to barometers and thermometers. And what you can do is you can do those. You can use those two types of measurements uh, with gases. And we talked about gases at the beginning of the semester. Uh, you can measure pressure, okay, in a gas. You can measure pressure, and you can measure volume and temperature. And this is the most elementary types of measurements that we did in science in the early 1800s. And out of that, we actually were able to start developing what we know is chemistry. Before 1800, chemistry was not a science. I have a Encyclopedia Britannica from like 1770, but not the original copy, but a duplicate of the original copy, and um, and there's only 3 volumes. Okay, and so these are encyclopedias. Okay, so I don't know if you ever seen the Encyclopedia Britannica. There's about 20 volumes. Each volume is over 1,000 pages long. It was Google before Google was Google. All right, and so if you want to look something up, you got to encyclopedia, open it up and look it up. All right, so that encyclopedia was first made in the early 1700s on a printing press, which was technology, and that kind of changed the whole world and changed revolutions. I mean, actually led to revolutions. But anyways, and it had all the sciences. And so when I look at this, when I look at my Encyclopedia Britannica from that time, it has physics, it has biology, it has anatomy, but there's no chemistry. 1780, there's no such thing as chemistry. There's alchemy, all right, which actually could be the beginning of chemistry, but there's no chemistry. So chemistry really didn't become a science until about 1820, somewhere around there. Okay, so this is a new science. We always people did chemistry, but they didn't know how to define it. Okay, so let's get into this. Okay, so one of the first people to do experiments with our glassware that really made some significant discoveries was John Dalton. He was a Scotsman. He was I guess just a school teacher, and in his spare time he played around with glassware, and he measured pressure and volume, as you remember, and when we covered gases, we covered Dalton's law of partial pressure. He came up with that, but also he came up with the idea of an atom. Before atoms, it was pretty much thought that things were made out of qualities, like you had something was red or hard or hot, or had water quality or earth quality or things like that. They didn't think that things were broken up into smaller and smaller parts. Maybe they did, but it didn't matter. This is that the quality of a thing was more important uh, than the parts it was made of. But through some experiments that Dalton did, he specifically looking at water, he broke apart. He was able to take water and break it up into hydrogen and oxygen. He came up with the idea of an atom. And his theory said all substances are made of atoms. Atoms are small particles that cannot be created or divided or destroyed. That means they're indivisible and solid. Solid and indivisible. Okay. Every element has its own type of atom, and the atoms of elements can come together to form new substances, like hydrogen and oxygen atoms can form water. Now, so he came up with this idea of the atoms, Now, it wasn't like he wrote something up and everybody goes, aha, we're all going to go call everything made out of atoms. No, it's kind of stashed away. People really didn't quite uh, believe that because they didn't need to. Okay. There was no reason to move away from their old ideas. Uh, and actually, his idea just kind of floated around and really wasn't considered done, proved until several years later. So this was like 1810 that he came up with this. So, but and people didn't really think about it. I mean, the scientists were working on all kinds of things. They were working on steam engines, and there's not like today's scientists. You can't go into they back then. Didn't say I'm going to become a scientist. You just did science. You decided, oh, I like science. I'm gonna go do it. So so that's kind of the thing. So, all right, just an interlude here, and this is going to be important as we go along. It relates to what we just talked about. Is we got to start talking about this guy named Einstein, and he's probably the most well-known scientist ever to be. Okay, I don't know who else is next to him. Maybe Newton. Okay, for you guys, if somebody asks you what science, who's the most famous scientist, maybe you'd say Einstein. It's not Elon Musk. Okay, he's not a scientist. Um, and maybe Stephen Hawkins. Hawkins is somebody you can pick as well, but Einstein is really the dude. All right, and the thing that made him so famous, okay, was in 1905, after he got his PhD, he could not get a job as a professor at a university. So he took a job at a patent office in Switzerland. And while he was there, he did his job, but on the side, he'd play around with problems that were in science. And in 1905, he wrote 4 papers that have been called the Annus Mirabilis papers. This means the year of the miracle papers. And he came with 4 papers, have to do with these 4 subjects here: Brownian motion, photoelectric effect, theory of relativity, and E equals mc squared. Okay. Now, we'll start right here. So this miracle year is 1905. It was Einstein that actually proved that atoms exist. So almost 100 years after Dalton came up with the idea, Einstein wrote this paper concerning Brownian motion. And if you want, you can look that up. But it actually proves that atoms and molecules exist. Okay. So, what we're going to see is that we're going to be using number 2, photoelectric effect, and we're also going to be talking about the theory of relativity. Now, we won't talk about E equals mc squared. That's more of nuclear chemistry, which if you take Chem 122, we'll talk about that. Basically, this is what led to nuclear energy and the nuclear bombs. All right, so just giving you a heads up of what to pay attention to. Okay, so here's what Einstein, he says Brownian motion basically proved that Dalton's idea was correct. Okay. All right, so we will look at the photoelectric effect as well, and theory of relativity when we move on during our discussion here. Okay, all right. So some people, some scientists took the took the idea of atoms to serious. And one of them was J.J. Thomson. He worked in England, Cambridge University. And what he did is he studied a new particle that was discovered called the electron. Okay, and basically he proved that atom can be divided into smaller parts, so it wasn't indivisible anymore. He discovered electrons. And we'll get all of this in a minute, but he won a Nobel Prize for his work. This is about 1897. So really there wasn't much work done on atoms until from about 1800 and almost 100 years. People really, and that's because they didn't have the technology to do it. And one of the things that made Thomson be able to do the discoveries he did was because of electricity. Okay, and so electricity, what he did was he took a glass tube, all right, and in that glass tube, he put some kind of gas, and then he attached it to an electrical connection, and then turned on the electricity, and when it did, it lit up. Okay, and gave off light. So what he wanted to do is explain why it gave off light. Okay, and his idea was this is that he said there was atoms inside, bouncing around inside that gas tube, and then when you turn on the electricity, what happened was the atom had electrons in it, embedded inside the atom. And when the electricity hit the electrons will fly off and create light. So he came up with this idea that reminded of him something in England called the plum pudding, where I guess this is a Christmas treat, where you have like raisins inside a bread, like raisin bread. And so these would be like the electrons, and the bread in the other part would be positively charged. Okay, because what he said is that when you turn off the lights, there was no more light. I mean, when you turn off the electricity, there's no more light. Therefore, it went back to a neutral state. So he said that the electrons were negative charged, and he could have said positive charge, but he called it negative charge. And I can't remember exactly why he did that. I think it had to do with something with magnetism. But he said if an atom has a certain amount of negative charge, it has the equal positive charge. And so he said the rest of it was equal positive charge. And he didn't call like protons or anything like that. So he said there's like 15 electrons in here. There would be a plus positive charged gel. So it's still solid, and you have electrons embedded inside this atom. One of J.J. Thomson's students, a guy named Ernest Rutherford, worked at Cambridge, and he decided to study the atom a little bit further. And what he wanted to do is he wanted to prove Thomson's model true, as well as Dalton's model is true. Is that it's indivisible, and that could be maybe we can figure out how big it is and so forth. And the technology that he used, again, new discoveries are from new technology. The new technology at this time, so this is like 10 years later, 1908, is the radioactive material. So Marie Curie had discovered that certain substances give off energy without any help at all, and they give off, if they give off energy, they give off particles. and the particle that the materials gave off um, were called alpha particles. And the alpha particles were found to have opposite charge of electrons and be quite bigger than electrons. Okay, so they're like bowling balls compared to marbles, but they had equal charges. Okay, so uh, and we'll see what those are in a few minutes. But back then they just call them alpha particles. So Rutherford wanted to study the structure of an atom by firing alpha particles at atoms. And so what he did was he wanted to take a fire streams of positively charged particles called alpha particles and a thin sheet of gold foil, 2,000 atoms thick about. And the idea was this: so you have his alpha particle gun, and they fire the alpha particles at a gold foil, and they would pass through, okay, or they would be reflected, but he pretty much expected them to just pass through. And what he'd want to do is he'd have a screen back here, and that screen would identify where the particles hit. Okay, now the genius behind this was sort of serendipitous, is he put other screens around as well. Now, he only thought that he would have, when he fired the alpha particles, they would fly right through, and I'll explain that in a second, why they do that, and hit this screen here. There's no reason why he thought he should put these guys up. He probably just thought as a last second thing, he just put them up there just to make sure. Okay, so let's see what happens. So he expected the positively charged bullets to pass right through the gold atoms in a sheet of gold metal without changing course at all. Because they're heavy, they're really heavy, and they just fly through, splash, all right? However, every once in a while, he found is that there was a indication of a particle being reflected back on one of the other screens, not the back screen. Okay, so he fired it at the back screen. Okay, and most of them going through the gold foil, most of them hit the back screen. But every once in a while, maybe like 1 out of 1,000, it would hit the other screen, or even bounce all the way back and hit the screen back here. And because of that, he thought, whatever it's hitting, it's got to hit it right on, bing, and then bounce right back, okay? But most of the time, it just flies right through. Okay. So from that, he came up with a different idea than ever been defined before. His idea was this: is that an atom is made of a central nucleus that has a positively charged particle, just like the alpha particle. And then, so if you fire the alpha particle at the atom, most of the time it's just going to fly through without hitting that piece. Okay, but every once in a while you get a very precise, you hit it, and because it's positively charged, same mass, it's going to bounce back and reflect. Okay, right. And so what he came up with is that an atom is not solid anymore. It's made out of a proton, a very, very small proton, protons in the nucleus. He called them protons. He didn't know about neutrons until the 1930s. And he said the rest of the atom had electrons flying around the protons, but most of an atom is empty space. Okay, no longer was it solid. All right. Now, intuitively, this doesn't make sense. All right, because if we have solids. If you take your hand and hit it against a wall, it seems solid. So it seems like atoms are solid. So it turns out the reason why your hand doesn't go through a wall is because the outside of your hands have electrons, and the walls have electrons. And electrons repel each other, and then that causes a push away from each other. It's not because it's solid. So this is a pretty cool paradigm shift. I mean, if you think about it, all right, we go from something that's completely solid to something that's almost completely empty. All right, so Rutherford basically said is the atom is protons with the electrons swarming around the protons like bees in around uh, um, a hive. Okay, now there's a problem with this. Okay, what is the problem? The problem is this: is right now so it's sort of like the Earth going around the sun. Okay, so you have the sun here and Earth. Now, so the Earth is spinning. I mean, the Earth is moving in a circle. That means it's changing direction all the time. Now, when thinking about Newton's law of motion, one of the first law says is that to change the direction of of something that's moving or not moving, change the direction or the speed of something, you have to apply a force, and that means they have to accelerate it. All right. Now, if you accelerate it, you apply a force, and a force leads to energy. Okay, because energy is equal to force times distance. We talked about that earlier, and so as this particle is moving, it is giving off energy. All right. So as it goes around the inner orbit, in fact, if it's moving at all, it's giving off energy, right? Now, there's a problem with that, is that just think if it's moving in an orbit, if it's giving off energy, that means it's losing speed, okay? Because energy is equal to 1/2 mv squared, and if you lose the energy, you're losing velocity. And if you're losing velocity, you're losing the ability to stay away from the nucleus. So the atom electrons start to get closer and closer and closer. And then eventually, it keeps on losing speed, the electrons would collapse in. Okay. The problem with that is electrons don't collapse. They are out in protons. Otherwise, atoms wouldn't exist. We know that electrons are away from protons. Okay, the paradox here is that they should be losing energy and slowing down, therefore getting to the nucleus, but they're not. Okay, so that's our problem, and we'll see how that is resolved later in the slides coming up. All right. Now, before we move on to next thing, let's go and talk about Einstein a little bit. We'll come back to the Rutherford's idea a little bit, but Einstein, in one of his Annus Mirabilis papers, theory of relativity said that the speed of light is constant. Okay, Einstein explained that there was two guys that came up with the experiment, Michelson Morley, and they were trying to prove that there was something called ether that light moves through, because light, it was considered a wave, and waves have to move through mediums, and like water, waves have to move through water. So these two guys were trying to find the material that light wades through, and they weren't able really to find it. Okay, and Einstein said, "Well, heck, maybe it's not there." And so he said it's not there, and through that he just said that the speed of light never changes, and that's a really cool thing. Okay, if you get a chance, look up the theory of relativity and all the fun things that come out of that. All right. So the speed of light is determined to be 2.9998 times 10 to the 8 meters per second. I'll just say 3 and 10 to the 8 meters per second. And we're going to get into this in a second here. Frequency and wavelength. All right. So light was light was determined to be a electromagnetic wave by James Maxwell. And James Maxwell came up with the whole ideas of all the equations for electricity and magnetism. He doesn't get enough props as he should. His work is right up there with Newton and Einstein. Is probably some of the most amazing math, science there's ever been. So if you get a chance, look up James Maxwell, about 1860 or something, English fella. But not that this has to do with him right now, but he came up with the idea that light was a wave. So what are some of the properties of waves? Well, waves aren't matter, but they carry energy. Okay, so if you have water, if you have, your water and then you drop a pebble in the water, what happens is that it'll produce waves, and the waves will go up and down, and they move, okay, but the water doesn't move, right? So if you have a bobber, and you drop this pebble in the water, your bobber doesn't move with the waves; it just moves up and down. So what moves? Well, what moves is the waves, and the waves carry energy. Okay, how big the wave is, the amplitude, is how big the energy. And we'll see this again. Again, waves were move through mediums, like water moves through water waves move through water, and like I said in a previous slide, it turns out that light doesn't do that, but it's still a wave. But a property of a wave is the speed of a wave. So as it moves this way, depends on how wide the wavelength is and how fast it goes up and down. So the way that I kind of think about this is like if you're walking or running. So if you're walking, you have a certain stride length, and you have a certain frequency. So, for instance, if you're like a giraffe, you have a really long stride length, and that would be like your wavelength. And if you were like a mouse, you'd have a very short wavelength, stride length, but a really high frequency. And both of these can change your speed. So if you want to go faster, there's two different ways you can go faster. You could either make your wavelength, your stride length longer, or you can go up and down faster. So if you had a if you had a giraffe with the speed of the mouse, you got a really fast guy. So what you have is the speed of a wave. Okay, C will stand for speed, is equal to the wavelength times how fast it goes up and down, called the frequency. All right, so now let's apply this to light. Because light, it was considered a wave from Maxwell's discovery. Okay, first thing he said And the speed of light is constant. Theory of relativity. We know the speed of wave is wavelength times frequency. The light that we see, okay, is part of electromagnetic spectrum. So electromagnetic spectrum also includes X-rays, magnetic microwaves, ultraviolet rays, infrared, and so forth. And we'll see that in a little bit. And like I said, light was thought to be a wave based on Maxwell's work. And so what you have is this equation here. It's the speed of light is equal to its wavelength, lambda, times its frequency. Okay, this has got to. All right, so if we look at the spectrum, electromagnetic spectrum, we get, so here's the visible light spectrum, and so you have gamma rays, X-rays. So these are and going down the other side. So these guys are super violet. If you could look at them, they'd be very, 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 very violet colored. And then you have your reds down here, radio waves and so forth. And we'll talk about how that relates to this up here on the slides coming up. But let's take a look at using our formula. C equals lambda times nu. Okay, wavelength times frequency. So the visible light spectrum is between 400 and 700 nanometers, or close to that. So from violet to red. Okay, it's that spectrum. So what is a nanometer? So nm is a nanometer, which is 10 to the minus 9th. So 400 nanometers is equal to 4.0 times 10 a second. Nanometers 10 to the minus 9th. So 400 nanometers is the same thing as 4 times 10 to the minus 7 meters. Okay. Now, we typically, when you do studies on spectrums, you usually use nanometers. Now, there's another unit called the angstrom. It's like this, which is 10 to the minus 10th meters. But we hardly use that anymore. Okay, so let's say I want to find, this should be new. So find the frequency. So what I want to do is find the frequency of this wavelength. So I'm given this equation. C is constant. So nu frequency is equal to C divided by the wavelength. So I plug everything in, and I get the frequency is 7.5 times 10 to the 16 cycles per second. Okay. Right. Now, one thing you'll notice, because the speed of light is constant, if the wavelength goes up, the frequency goes down. And the other way is true, as well. As the wavelength goes down, the frequency will go up. So a long wavelength will have low frequency. Big, this is big, this is small. And a short wavelength, small, will give a high frequency. Okay, so if you look up here, these guys over here are high frequency, small wavelength. These guys are low frequency, long. And the reason that is because the speed of light is constant. Therefore, as one of these guys changes, the other one has to change inversely.